Hiya, thanks for joining us. In this presentation we'll explain the drivers behind the ARM's open source software group's move to Kubernetes. We'll also introduce the technologies used and the challenges each of those addressed. Finally, we'd like to discuss the benefits we believe this brings to ARM. But before we do that, let me introduce myself and the team. I'm Dean Arnold. I lead the globally distributed DevOps and infrastructure team within the open source software group at ARM. Our group is responsible for all the services and tooling that enables the open source group to collaborate with upstream projects. I'm also part of a wider DevOps leadership team helping to drive standardization and adoption of tooling across ARM's engineering community. Today I'm also here with Colin Thorbenson. Colin leads our lab and on-premise infrastructure management. This includes geo-distributed test farms made up of development boards, vendor devices and server hardware. In addition to this, Colin is driving our engagement with SUSE around cloud deployments and SUSE Manager. Although Colin and I are presenting our journey, this is far from something we did alone. This has been a collaboration with both SUSE and multiple groups across ARM, allowing us to learn and benefit from a wide range of skills and expertise. We'd like to thank everyone listed on this slide, plus any others we've possibly missed. I will now hand over to Colin, who will cover the challenges we faced which led to this journey.
Thanks, Dean. Our ARM-shaped open source dilemma falls into three main categories: security, diversity, and ARM on ARM. Let's kick this off by talking about security and how it affects our workflows. Okay, so saying open source workflows are bad for security is us being dramatic. The nature of open source means it's available for public contribution. While most patches are legitimate, there are no guarantee that code submitted isn't malicious or inadvertently introducing security problems. These problems may range from code being built to issues with the CI/CD pipelines or affecting the IAC underlying infrastructure. Open source projects are diverse, covering a large number of areas. In each of those areas there are project-specific methodologies with different implementations leading to a larger tap plane and a wider margin for error. Diversity makes policing of infrastructure challenging, and remediation work is often not straightforward, as we may require various methods to roll out patches or security fixes. Due to public contributors, there's a vast number of engineers leading to a large range of different practices and approaches to solutions. Engineers face a wide range of challenges themselves, ranging from tight deadlines to resource constraints, so there is a real need to deliver in the most efficient manner possible. This can lead to taking the shortest path, which may not be the best path, or with security in mind. As touched upon, open source workflows can be extremely diverse. Different projects have differing requirements, and while it can be common for there to be functionality overlap, these projects are usually managed and maintained by different groups of engineers. Engineers will also naturally have their own preference and comfort, and this can lead to various tooling being used. Projects can differ in their stages of development. More mature projects may have a wide-reaching community established with more effective security practices and reliable IAC. Less mature projects may not have the community or engineering availability to prioritize security and reliability over core functionality. This presents us with the challenge of understanding the needs and requirements of each individual project. This can have a direct impact on the quality of a project. Smaller communities may not have the same reach of a larger project, which can more heavily rely on its community contributions for its security and continuous improvements. There can be a lot of reinventing the wheel, leading to more administration that requires learning different systems. At times, we may need to adjust our infrastructure to match the different approaches of deploying open source projects. We want to be developing for ARM, on ARM, by ARM. Where we can, we want to be running all of our workflows using ARM. We acknowledge that this isn't always practical, so where required, we will use alternative architectures. Cross-compiling for ARM is great, but it can miss some of the nuances with the architecture, so we would like to see projects being built natively on ARM. We want to prove that ARM runs real-world workflows in the data center, and we would like to see ARM available in all aspects of the software ecosystem.
As you can imagine, this felt like quite a beast of a problem to tackle. Not only did we have to cater for the needs of our own team around maintenance and management of solutions, we also had to look after the engineering teams, providing them the freedom they needed, plus make sure we was compliant with ARM security policies and their strategy around using the ARM architecture for our own development. So in order to do this, we had to work out 4 key ways in which to tackle the problem. The first of these was to narrow the scope. By this we mean reducing things down into a smaller subset of tools in order to reduce maintenance overhead. This is essential for our team as we're providing the infrastructure that these teams need. With an ever-growing, diverse range of projects, we're never going to get to be in a position where we can manage things sensibly unless we reduce this and really become experts in fewer tools rather than being okay at a large number. We then need to be able to provide autonomy. This will allow our engineers to have the freedom they need. Again, they're working directly with these open source projects. They've got a better understanding of the needs, and as discussed before, we're not able to cater for every single configuration and tool, and it's not possible. So we need to be able to give the engineers the capabilities to deploy them themselves, but run on top of something which we know is conform and secure and reliable. So in order to do that, we're going to take a zero trust approach. We need to make sure our workloads are secure and also our infrastructure, because with some of the things that Colin discussed previously, we're not guaranteed that patches aren't malicious. We're not guaranteed that changes to the infrastructure couldn't potentially cause problems, whether this is on purpose or by accident. So one of the things we need to do here is sort of reduce the blast radius and make sure that the engineers are able to run the workflows they need using the tools and configuration from upstream, but this doesn't directly impact ARM and our IT services and things. And then the final piece of this is that we need to do it all on ARM. ARM's strategy is to make more use of ARM architecture for our own development, and so our stance is to take the infrastructure that we use today and make sure that it's ARM by default, and the only use of another architecture is where a project needs it specifically for their requirements. So in order to do this, we looked at multiple things available, and we chose to go down the route of working with SUSE. So why did we choose SUSE? Basically, their stack was very close to offering us everything we needed in terms of technical solutions, from the management layer, the infrastructure, and right down to the security and client tooling. It also has been proven to integrate with other applications and services that we use today. A good proportion of this stack was already working on ARM, with some of it already commercially supported, and this is vital in our goal to use ARM architecture by default for everything we do. This entire stack was also based upon existing open source projects with an active community, and as an open source group this was music to our ears as it allowed us to contribute directly. There has also been a real willingness from SUSE to engage with us on this journey, which has really helped the collaboration and progress. As this entire stack is based upon open source projects, why are we going for a commercial offering? So just because we're part of the open source team and we provide support and infrastructure for open source engineers working on open source projects, it doesn't mean we can't use a commercial offering where it makes most business sense. One of the reasons being our engineering team is not equipped for 24/7, 365 days a year support. It's just not possible. So having this enterprise support is vital to use when business critical issues arise. Commissioning solutions to production level is also time consuming and requires upskilling of our engineering teams. This upskilling is provided through the training that is provided as part of our enterprise contract. New technology also presents us with a greater risk of error or poor implementation at early stages of the project. Being able to pull on the advice and expertise of the SUSE professional services team ensures we are making sensible engineering decisions from the off. Also, using SUSE's enterprise-grade solution provides us with the confidence of a trusted supply chain and security hardening of our infrastructure. And I think the main thing is that this mix of open source and commercial support also allows us to directly contribute and collaborate with both SUSE and the wider engineering community. A good example of this being the ongoing work around ARM enablement on a number of the Rancher stack components. We realised quite early on in this process that the large number of different solutions and workflows were having quite a direct impact on the efficiency of both our team and the engineering teams we support. To tackle this, we really needed to reduce the number of different tools into a smaller, more manageable subset, but not take away too much freedom from the engineering teams. The reason being that we still needed to be flexible enough to align with the tools and systems used by the upstream projects. By reducing the number of tools, that meant we were able to upskill our engineers into a smaller subset of tools rather than spreading the expertise too thinly across the existing things that we use today. As a lot of projects we work with do have containerized tooling and infrastructure, we felt like Kubernetes was a sensible approach which would probably cover roughly 75% of our workloads. By using Kubernetes, it also meant that we were easily able to move to different platforms behind the scenes. This meant that we could write a thin layer on how do we deploy Kubernetes in, say, AWS or Google Cloud. And this means that we could do that once, then everything above that could be reused. This would be much more efficient for delivering our solutions and meaning that we'd be able to bring projects up to speed and get them started in a far quicker fashion. In this slide we have an overview of SUSE's Rancher Prime offering. As you can see, we have the Rancher Prime Manager, which allows us to manage, view, maintain and allocate resources across our entire compute estate. Beneath that we have the downstream infrastructure services which make up the bulk of our compute. On-premise, public cloud and edge solutions are all supported, which gives us the flexibility we need for our diverse workflows. One of the benefits of using Rancher Prime for public cloud is that Rancher already provides full cluster lifecycle support for a good percentage of cloud-based Kubernetes services. These include EKS, AKS and GKE. This simplifies onboarding of new cloud platforms for us, as we do not have to build the Kubernetes clusters ourselves from scratch for each new cloud provider. For on-prem compute, Rancher integrates with established VM solutions such as VMware. They also provide their own hyper-converged infrastructure solution in the form of Harvester, which again integrates nicely, allowing us to provision VMs and the Kubernetes clusters that run on top of them. NewVector then gives us a security solution to protect all parts of the stack. We will discuss this in more detail later on in the presentation. And as you can see on the right, we have the 24/7, 365-day-a-year support and professional services. These give us the confidence we need around seeking advice for maintenance, deployment and day-to-day support activities. Rancher Prime does also provide a trusted registry, though we're yet to switch over to that today. Now we've covered the SUSE offering, let's discuss how this applies to our specific setup. The first part is the Rancher Management Server, which we've deployed today on AWS using a Graviton 3 based EKS cluster. We do have plans to deploy this in other regions and possibly also other cloud providers. We then have a split of public and private cloud deployments as our downstream clusters. For our public cloud deployments, we have a mixture of different providers available to us, including AWS, GCP, Azure and Alibaba. This also presents us with a mix of architectures depending on the needs of the projects. In order to simplify things, as these are already supported in Rancher Prime, we chose to use the Kubernetes services made available by each cloud provider. For the private cloud, we've deployed a multi-arch Harvester cluster and we are running K3s on top of this for Kubernetes. We are then making use of SUSE Linux for our compute nodes and we're using NewVector to secure all of our Kubernetes clusters. Finally, we chose to use SUSE Manager to manage the provisioning and lifecycle of our bare metal compute. For public cloud, autoscaling groups mean that we can update our images and ensure patching is up to date that way. But for private cloud, we need a different strategy. This is due to the persistent nature of the nodes. To tackle this, we will make use of SUSE Manager to ensure the OS is up to date. When it comes to our engineering teams, we don't want to become a bottleneck for them. Therefore, we want to provide as much autonomy as possible for them so that they can manage their own compute and configure it in a way that meets their project needs. However, we don't want a free-for-all, as this would reverse all the work done to reduce the number of tools and different approaches used today. Therefore, we designed a solution which would hopefully provide the freedom needed but allow us to limit the diversity and ensure workloads are secure and compliant with company policy. For starters, we needed to manage the underlying platforms. For this, we used SUSE Manager. This was used to manage the bare metal estate and we used Harvest to manage our VMs. SUSE Manager is also being used to provision the VM clusters themselves. We can then use it to carry out system auditing and patching of both our physical and virtual compute. Harvester is integrated with Rancher, which allows us to allocate quotas at both the hypervisor level but also at the Kubernetes layer. This means we were able to implement a solution which provides self-service capabilities, meaning the engineers can log into Rancher and deploy both their VMs and the Kubernetes clusters that run on top. The Rancher integration means that we can also make use of Fleet, which enables continuous deployment of applications in our Kubernetes clusters. To do this, we've taken the approach of splitting the deployments into two main categories: project workloads and core applications. This allows the engineers to deploy what's needed for their project, but by us deploying core applications into all clusters by default, it means we're able to ensure security and admission control tooling such as NuVector and KubeWarden are delivered out of the box. It also means we're able to provide observability tooling and integration with key services such as GitLab, Vault, and Artifactory. By giving our engineers direct access to their own resources in Rancher and SUSE Manager, our aim is to be as transparent as possible and provide the teams with the visibility they need for vulnerabilities, performance, compute utilization. This allows the teams to debug and better understand their own infrastructure. As mentioned, one of our key goals was to provide self-service Kubernetes environments which were secure and which also conformed with company policy. To do this, we implemented the setup as shown on this slide. The engineering teams and admins are able to manage the full deployment of a cluster using a mixture of Rancher Management Server and GitLab. As you can see, Rancher manages the deployment of the underlying compute nodes, and to do that it uses Harvester, and then on top it is able to deploy the Kubernetes clusters. In this case we're using K3s. We'd ideally like to use RKE2, however I don't believe this is available for the ARM architecture today. We're also looking at how we can automate the registering of nodes with SUSE Manager. This will allow us to do the patch management, and we're looking at how we can modify the containerd settings at deployment level so that we can use our Artifactory instance as a pull-through cache. Once the clusters are deployed, Fleet then can pull the configuration bundles for our core applications and apply them to the cluster. These include Prometheus to provide observability, and we're looking at how we can make use of the Rancher UI so that the engineering teams are able to view their metrics. We can then also deploy Cert Manager and External Secrets Operator and configure both of these to talk to our Vault instance. And then for workloads that need it, we're able to deploy Longhorn for storage and also load balancers. We then also ensure that NuVector and KubeWarden are deployed to provide admission control, process protection and vulnerability scanning of nodes, the containers and also the network. And we're looking at how we can use Valero to provide backups to things such as S3 or on-prem storage. At this point, the engineering teams are then able to deploy their applications. So to do this, they can either follow the same approach as we've done for our core applications and use Fleet, or they can deploy their own CD tooling such as Argo. It's also possible for them to use the Rancher UI and use the Rancher app catalogs to deploy things which they've registered themselves. So the diagram on this slide, as you can see, shows how we've done this for an on-prem deployment using Harvester. However, we do also follow a similar approach for public cloud hosted clusters. So for things such as EKS or GKE, the key difference being that the node drivers and the cluster drivers I don't believe are available for ARM today. So for that we use Terraform to provision our clusters, and we use the Rancher Terraform provider to register the cluster with the Rancher Management Server once it's complete. At this point, all the application deployments and integration follows the same pattern as it does on the on-prem solution in the diagram. Now that we have our clusters deployed, we can take a look at how we secure them and the applications that run on top of them.
Ensuring our workloads are secure is vital to our success. A good starting point for this is ensuring that RBAC is enabled throughout the entire stack. We need to ensure that all common and shared credentials are removed and that we use one of the various trusted ARM methods of authentication. We are able to provide compute to our engineers quickly in the form of VMs using Harvester. This removes the need for shared resource amongst engineers. We can enforce trusted images with standardized security tooling and configuration using either SUSE Manager's Configuration Manager or Cloud Init scripts run directly from Harvester. It's very easy to allow our engineering systems, both physical and virtual, to fall behind on security patching. SUSE Manager lets us force critical system patching onto all systems in an automated fashion. This allows engineering teams autonomy over non-critical system patches and updates, deciding whether they are required or not. Combined with using SUSE Manager, we are moving our core services onto SUSE Linux operating systems. This gives us an opportunity to combine SUSE Manager and SUSE Linux to ensure complete system security, reliability and visibility. As well as using RBAC, we can implement zero trust controls using Rancher, ensuring that we offer a balance of visibility within our clusters to our engineering teams, without giving too many permissions to allow them to make direct changes to the cluster. The built-in monitoring tooling such as Prometheus and Grafana will integrate with our existing monitoring stack. KubeWarden allows us to set policies for pods. As an example of this, we can ensure that all images on our cluster are from our trusted registry. We will go further into NewVector in the next slide. It's going to be an integral part of securing our infrastructure. Using the approach of never trust and always verify along with the methodology of 4 steps of security, we use NewVector to manage our Kubernetes clusters. By protecting the perimeter of our Kubernetes deployments, we can ensure that all nodes, clusters and pods are secure. Authentication and authorization gives us the opportunity to limit the functionality within our nodes and pods. Using process blocking, we can ensure that all the commands being run are trusted, and if any malicious code was to run, it would not be able to do any lasting damage. Denial offers visibility over our network traffic using ingress and egress rules between pods, containers and nodes. Continuous monitoring gives us full visibility into how different pods within the cluster are working. This can help us understand how our engineers are using our infrastructure. NewVector is still very new technology to us, so we are still learning it, but we can easily see the huge benefits it's going to provide us. And as NewVector is container-based, we will be able to deploy across all of our clusters in an automated fashion as we've previously discussed. Now we will discuss where we are on our journey of adopting these new technologies. As you can tell, we're still at the start of our journey. Our legacy infrastructure isn't amazing, but it did a good job. We know it needs improving, which is why we are making changes. Our manual deployment methods were inflexible and they were often easily not reproducible. This meant that expertise was limited to a small number of people, and this could lead to bottlenecks and single points of failure. We've proven a Kubernetes-based environment over multiple cloud providers, all of which being managed by Rancher Prime. In addition, we've proven a private cloud environment using Harvester and K3s. We're starting to build a fleet-based approach to managing our cluster applications, and we have ongoing investigations around how we can effectively use NewVector to secure our workflows. Our approach is ARM by default, but using alternative architectures where project dependent. We are classing this as tech preview, as not everything is ready for a multi-arch deployment, and we are taking strides to address any gaps in our stack, working alongside SUSE where necessary. This is the first step towards our end goal, where we will continue to build on our strong working relationship between SUSE and ARM with a focus on wider ARM enablement. We will have migrated all of our project teams to these new technologies and therefore reducing our legacy infrastructure. And finally, we have a strong desire to create an open source community so our engineers can feel more empowered to make changes and provide feedback to the solutions that we are providing. So the big question is, did we tame the beast? Well, ish. The beast isn't fully tamed. As a team, we now have a much deeper knowledge in a smaller number of tools. This is due to us moving more of our projects to Kubernetes. We have created good, reliable infrastructure that we trust, and we have developed a good route for easy adoption of new projects. When we have access to new cloud service providers, we have the ability to easily integrate them with our existing stack without needing to repeat engineering effort. We aren't quite there yet, but we are already seeing a lot of the benefits that this stack is going to provide us. We are now able to allocate resource and roles directly to our engineering teams. This gives them autonomy of their own quota. With the reduced delivery times this stack provides us, we are now able to spend more of our time working directly with our engineering teams. The stack integrates well with all of our existing authentication and authorization methods. This allows us to assign fine-grained role-based access controls across our estate. Having a combination of IAC and Fleet allows us to deploy a cluster with baked-in security tooling such as NewVector straight out of the box, and having a GitOps approach allows us to remedy issues in a wide-scale and automated fashion. Well, what works on ARM? So far, SUSE have done an amazing job of making products available natively to ARM. This includes Longhorn, Fleet, K3s, SUSE Linux, Rancher Desktop and BCI images. Rancher Prime is not classed as fully supported on ARM. This is due to additional functionality such as node drivers and applications within the app catalog not being supported. Some of the things we are currently working on is adding node driver support initially, focusing on Harvester. Other applications in the app catalogue, such as Longhorn and monitoring, have already been proven to work on ARM and integrate nicely with the UI. We currently have a local ARM build of Harvester running. From the limiting tested we have conducted, all core functionality is working as we would expect. We are looking to contribute these changes to the Harvester team in the near future. As of yet though, we have not tried a multi-arch deployment. Currently, Harvester clusters across multiple architectures must remain independent from one another. And as with Harvester, we also have an ARM build of NuVector. We have fully working images for the manager, the controller and the scanner. We have built the enforcer, however we are seeing some issues porting Hyperscan to VectorScan. We are in active discussions with the NuVector team and we are working to get ARM supported added in a future release. Today we are unable to run SUSE Manager servers or proxies on ARM, but it does manage ARM-based clients. In the future we would like to deploy our SUSE Manager servers and proxies using ARM-based Kubernetes clusters. In the end, we would like to see the entire SUSE catalogue available natively on ARM. We would like to take this opportunity to thank everybody in both SUSE and the wider community who has contributed to this work.